everyone. So today we'll cover 16.5 and curl and divergence. We'll start with the curl of a vector. And so the curl of a vector is a vector. I have to point that out. The curl of a vector, we can think it's vector field, will be a vector. It's defined as del cross F. Okay, what the heck is del? Up until now, I've always been writing this del with like a function like this, like gradient of a function. But this is the first time that I'm referring to the del alone. So make a note, when I'm talking about del, I'm just saying delta, delta x, or delta, delta y, or delta, delta z. Or if you want to call these d's, ddx, ddy, ddz. So if we had a vector field, let's say F equals, I'll give you one. I'm actually taking this example from the book. Let's say the vector field is xz. All right, there's the x component. It's three-dimensional, x, y, z. And negative y squared. We're going to find the curl of this vector field. Well, it's going to be a vector. So we'll get the curl and it'll be a vector. If you're curious what this is, people always ask. I want to read this section from the textbook. They said the curl vector is associated with rotation. For instance, when F represents this big F. When F represents the velocity field in fluid flow, particles near a point like x, y, z in the fluid tend to rotate about the axis that points in the direction of curl of F, which we're going to find. And the length of this curl vector is a measure of how quickly the particles move around the axis. So they said, for instance, if the curl of the vector field is 0 at a point P, then the fluid is free from rotations at P and is called irrotational at P. So it would have no rotation at that point. So if you're wondering what this is dealing with in terms of like fluid flow. But here's a vector field given to us. We're going to find the curl of F. What's defined as del cross F, the cross product of del cross F. So this is del, just del F. So I'm going to write out the matrix. How we always found the cross product of two vectors. I'll put I, J, and K. All right, there's my I, J, and K. I'm going to put the del first. Now del is just what? ddx, dy, ddz. Or if you want to write delta, delta x, delta, 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 delta. That's what I'm going to put for del. F is, I got enough room here. This is xz. The y component is xyz, and the z component is negative y squared. And we're going to do this just like we always did a cross product. And the cross product of two vectors is a vector. So, we're going to do the cross product. Behind that. What's the derivative of this with respect to y? Subtract the partial derivative of this with respect to z. That's what we'll put right here.
So negative 2y.
All right, negative 2y. Subtraction.
With z, right? You said? So
Yeah, the partial of that with respect to z.
xy.
xy. And here's my first component. We're finding the curl of vector field F. Okay, cool, got it. The middle component, isn't that where we change the sign? So I'm going to get it ready, like negative. Ready, all right, wipe out the middle column. What's the partial of that with respect to x? Well, like that.
xy squared?
What's the partial of the negative y squared with respect to x? Doesn't have an x in it.
So
0, right?
Yeah.
All right, so we'll get 0 subtraction the partial of that with respect to a z.
x.
So I get 0, I'm going to write it, minus x. So we knows I actually got a 0 when I did that. So let's see when I wipe out that middle column. Partial of that with respect to x minus partial of that with respect to z. And how about the last component? We'll wipe this k column out, get that out of the way. What's partial of that with respect to x minus the partial derivative of that with respect to y?
yz.
yz minus 0. I like it. You just found the curl of vector field F. I guess I could simplify it a little bit. What? Negative 2y minus xy, x, right? Isn't that just x? And then yz. That's just the curl. Is that okay with that? Well, we'll do something also today called the divergence, but we're going to stick with the curl for a while because it can be very helpful. It can be very helpful. Remember the word conservative vector fields? Good. So it comes into play with conservative vector fields, the curl. Here it did. Like, that wasn't so great, but I'm be curious. We'll look at some vector fields that might be conservative. So can I erase this? Try this one now. How about x squared, y squared, z squared? Just to do them up. So sometimes you get expressions like we just saw, but sometimes it comes out a lot easier. When the answer, I could say, would be more simple. So let's find the curl of this vector field. The vector field x squared, y squared, z squared. Well, I got my delta x, delta y, delta z. That's my del. And then I'll put the vector field f here. X squared, y squared, z squared. Let's find the curl of this vector field. So the curl of vector field f is, first component, wipe that out. What's partial root x respect to y minus partial root x respect to z?
0, 0.
I love it. Cool. I like it. Makes the math easier. This is the one where we're going to change the sign, so I'm going to get it ready. Now, what's partial root x respect to x minus partial root x respect to z?
Same, 0, 0.
0. And how about that last component?
Same, 0, 0.
Yeah. Partial root x respect to x, 0, minus partial root x respect to y.
0.
So this came out to be what we call the zero vector. And you can write it like that. Unless you want to write 0, 0, 0. We call it the zero vector. Well, there's a connection between conservative vector fields and the curl of the vector field. And here it is. And I think we should prove it. I'm going to make a statement, then we'll prove this. And if the curl of a vector field, bless you, if the curl of a vector field is 0, that means that vector field is conservative. Boy, is this awesome, because it gives us another way to check three-dimensional vector fields, and whether or not the vector field is conservative. Remember we were doing that last class? It's easy when you just have two-dimensional vectors. You know, we just check take that partial derivative, take that partial derivative, and see if they're equal. But when it's three, we always had to do three checks. Remember that? So we got a great way now. We're going to say, if the curl of the vector field is 0, then we know that that vector field is conservative. Now, we have to review something. I keep saying that. Students sometimes will go, time out. What is the definition of a conservative vector field? So I want to point out the definition of a conservative vector field is this. That the vector field is equal to the gradient of some functions. That's its definition. So I want to point out, this is what it means for a vector field to be conservative. That f equals del f. That's the definition of f being what? Is conservative. What do you mean for a vector field to be conservative? I'm saying there's a potential function that will exist, such that the partial derivatives of that function is equal to that vector field. That's another way to say that, but here's a very simple way to look at it. So when you agree, here I can write that, because of what we got. Remember what I said? If the curl of that vector field is 0, then that means the vector field is conservative, which one this one is. That means some function of f, a function f of x, y, and z must exist. So can we just quickly find that function? It shouldn't be too hard. And when this must exist, there must be some function of x, y, and z. This must exist. Somebody exists. It has to. Because the vector field is conservative. We showed that by getting this equal to 0. But can you find this function of x, y, and z? Remember what to do? This is where you integrate. We're saying we're saying this is the partial with respect to x, that's the partial with respect to y, that's the partial with z of some f. So you can integrate that with respect to an x. What would you get? X cubed over what?
3.
Plus, now integrate that with respect to y. If you get repeats, toss them. What's integral of that with respect to y.
Y cube over 3.
Alright, and lastly, remember what I expect to see? There you go, that's the function. I'll put constant K. Constant K. That's the function. That's the function, but that means we knew it existed because the curl of f equals 0. So can we do something? This is fun. Can we prove that the statement, if the curl of a vector field is equal to 0, or, excuse me, let me say it again. Can we prove if the vector field f is conservative, the curl of f equals 0? Let's do that. We're going to do a math proof. So here's our proof. We're going to prove this. When you do proofs, it helps you remember this. So we're going to prove the statement if some vector field is conservative, comma, the curl of a vector field, which is a vector, will always equal what?
0.
0. And I'm going to put a little vector symbol on there because it's really a vector, so 0 vector. All right, let's prove that. We just saw what happened. We noticed that the function did exist. Well, let's prove this. If a vector field is conservative, the curl of f equals 0. So I start with the curl definition. What's the curl of f? So I'm going to start there. Curl of f equals del cross f. If we're finding a curl of one, we got to start with the definition of the curl of a vector field. So far, so good? Every little proof has a crux move to it, where you slip in one little thing, and that proof's going to be real easy. Here's the crux move. If f is conservative, what does that mean? I'm going to go off to the side. If f is conservative, that means, I'll write this again, that f is equal to a what? Yeah, the del of f. Or gradient of f. If you like to put gradient of f, G-R-A-D, the gradient of some function. The gradient factor of that function. So, do me a favor. Substitute this right here. Aha, that's the crux move to the proof. Let's do the math on this. And let's see what we get. Alright, this is fun. I think you'll find it to be an easy proof. I'll line it up. I, J, K, delta X, delta Y, delta Z. Now, there's a couple ways I can write del F. I can write delta F, delta X, delta Y, and delta F, delta Y, and delta F, delta Z, right? I'm going to write that, but I'm going to erase it. I think you'll find it easier with the other notation. So I can write it like this. The book does that. But isn't that del F right there? I'm going to write it like this, though, because I think the writing, when it comes to our writing, when we write this proof, I think you'll find this easier. How about we just do this? That's easy to write. Let's write it that way. I just think it's easier. Are you ready? Get this curl. All ready. If f is conservative, prove that the curl of the vector field would always be 0. Are you ready? Wipe this out. The partial of this with respect to a y. Oh, I know what that means, right? That would be this. Minus the partial of this with respect to a z. Did everyone see what I just did? I'm going to do it again. So you go, what am I doing? I'm going to take the partial of this with respect to y. That means the second partial derivative. I'm going to take the partial of this with respect to a z. That's the second partial derivative. So I get that. Does anybody notice something already?
Conservative, yeah.
Yeah, these are equal. Pythagoras theorem, that's 0. Watch what happens in the middle. It's just going to continue, everyone. You ready? Wipe this out. FCX minus FXZ. And down in the third component, look what you get. FYX minus FXY. And by Clairaut's theorem, there you go. What do you get? We get, this is what? 0? What's that? negative 0, which is 0, and this is what? 0. We proved it. Here we can put a QED. Quite elegant. We can put the math column symbol. We ended the proof. There we go. That shows that's a 0 vector. The curl vector field is 0. Isn't that cool? So this is a great way of when now we have a great check to see, hey, is the vector field conservative? Let's find the curl of the vector field. I do point out it must be a 3-dimensional vector to do this because we're doing a cross product. So if you wanted to do it with a 2-dimensional vector, just make the z component a 0, right? You can do that. All right. So erase this, erase this, erase this. Great job with the proof. By the way, in terms of notes, I did put the proof on the back side of those notes if anybody wanted to see it. Because it's such a cool proof. Easy to do. I'm going to leave that up there. But I'm going to start with a problem from the practice problem. And the question is, can you determine whether or not the vector field is conservative? All right. Determine whether or not and I'll do number 15. Is conservative. I wrote be clear in your justification. Okay, we'll justify it. And as a part B, if the vector field is conservative, if F is conservative, find a function such that F, vector field F, is equal to del of